In this lecture, I'm gonna be talking about few-shot learning, but we are using margin. So we want to understand what a negative margin is. So I'm gonna be focusing on this important paper in 2020. This paper introduces a negative margin loss to metric learning-based few-shot learning methods. The negative margin loss significantly outperforms regular softmax loss and achieves state-of-the-art accuracy on 3 standard few-shot classification benchmarks with few bells and whistles. These results are contrary to the common practice in the metric learning field that the margin is 0 or positive. It's correct because most of the time we assume that there is no margin. And even if you use margin, it's positive. But in this paper, we focus on negative margin, which is interesting. To understand why the negative margin loss performs well for the few-shot classification, we analyze the discriminability of learned features with respect to different margins for training and novel classes, both empirically and theoretically. We find that although negative margin reduces the feature discriminability for training classes, it may also avoid falsely mapping samples of the same novel class to multiple peaks or clusters, and thus benefits the discrimination of novel classes. So there are 3 contributions in this paper. The first one is, this is the first endeavor to show that softmax loss with negative margin works surprisingly well on few-shot classification, which breaks the inherent understanding that marginal can only be limited to positive values. We provide insightful, intuitive explanation and a theoretical analysis about why negative margins works well for few-shot classification. The proposed approach with negative margin achieves state-of-the-art performance on 3 widely few-shot classification benchmarks. So in few-shot learning, we have, for example, CN-way K-shot learning. For example, 5 classes, and for each class we have K-shots, K examples. So in image classification, for example, the softmax loss is built upon the feature representation of deep network. So Z is just feature representation, and it's a backbone network with some parameter theta. And its corresponding label is Y sub I, this Y sub I, and the linear transform matrix W. So in recently introducing the large and positive margin parameter to softmax loss is widely explored in metric learning. So we directly integrate the margin parameter to the softmax loss to learn the transferable metrics, aiming at benefiting the few-shot classification in novel classes. The general formulation of large margin softmax loss is this loss. So S is just similarity between 2 input vectors. This S here, we want to have similarity between 2 input vectors. And you see M is just the margin. M here is margin. So we just minus M instead of plus M, minus M. And beta is temperature parameter. For it's about concentration issue. Because some of the scores are very large, so we concentrate around them. And it's worth noting noting that all the previous works in large margin softmax laws restrict the margin's positive values. So we formulate two instantiations with different similarity function. By taking the inner product similarity, the negative margin softmax logs could be obtained. By taking the cosine similarity, we can formulate the negative margin cosine similarity laws. In ProtonNet, I remember we used to calculate the distance between each of the representation and those centers. We call it proto centers. So the constant of distance in that original paper, I think it was in 2017, so we just subtract two vectors, and this is the constant of distance. Here they just use dot product of two vectors instead of differentiating it, instead of subtracting them. There are many different ways to create a kind of similarity. But this is not the main point of this paper. The main point is that we are using margin. So in this previous slide here, we are using its negative minus m, so that we are creating a margin for that. So we analyze the discriminability of deep features by the deep model with different margins to understand why negative margins works well on novel classes. We denote the pre-trained backbone network trained with margin parameter m as f theta. So for class J, in base class or novel classes, we have the set of examples labeled with class J. So these are pairs. And we compute the class center just as the mean of them. So it's like the usual ProtonNet that we calculate the mean. But this is important. We define the interclass variance and intra-class variance, two different variances. And then we say that if interclass variance becomes larger or interclass variance becomes smaller, the deep features would be more discriminative. So we follow to define the discriminative function as interclass variance divided by intraclass. So this is just interclass variance divided by intraclass. To measure the discriminability of deep features with different margins, we plot the interclass variance, interclass variance, and discriminative function with respect to margin m on both the base and novel classes of mini ImageNet. So you see the margin starts from negative to positive, and we do it for base classes as well as novel classes. This is the visualization of data distribution on angular space with different margins. Okay, so we see that if your margin is negative, you have a better data distribution. So we have images x and x prime with both of them. So it consists of a two-stage pre-training and fine-tuning. The negative margin softmax loss is integrated in pre-training for learning more transferable features with two types of similarities: inner product that I said and cosine similarity.